Hello everyone. I'm Bruce Calder. I am the VP of Consulting Services here at Claigan. Almost had a moment, forgot who I am, was, are, whichever. I'm going to talk about life cycle assessment and a little bit about the California SB 253, where some of this hits the mandatory side of things. So a little bit about life cycle assessment. What is life cycle assessment, also known as LCA? I remember the first time I saw an LCA presentation would have been in Vienna about 17 years ago. It was definitely in the realm, very popular in Europe at the time, definitely the realm of academic. It's come a long way since then. And so part of what we're going to talk about, it's come a long way from the purely academic, specialist point of view to more of a regularized whole thing, to the point where, even municipal and provincial or state level and country level governments use them themselves. LCA is the high level is a method for evaluating the full environmental impact of a product, process, or service from beginning to end. And there's a lot of ways to do it. There's a lot of ways to measure environmental impact. There's a lot of usually about emissions of things or what it does to the environment. However, you can set it up for different goals. Simpler, it's really the cradle to grave greenhouse gases emissions of a product. Now, it can be other outputs. There are other things. You see sometimes life cycle assessment for a laptop. You'll see it with other kinds of emissions like sulfur type emissions, etc. Greenhouse gas is usually the main one, the one most regulators are interested in. It's definitely the most commonly used, but you can look at environmental impacts different ways. So greenhouse gas is one of them. You could look at it in many other ways. Note, there are a lot of ways, again, to quantify the cradle-to-grave contribution of the life cycle of the product, but the most common is greenhouse gas emissions, GHG, in kilograms of carbon dioxide equivalent. They basically convert whatever energy or gas emissions or whatever the product's doing at whatever part of its life into kilograms of carbon dioxide equivalent. And that's the number you put at the end, and then each part from the cradle, the original like raw metal manufacturing to the end of life recycling, say, of a laptop, every piece of that has math or a process with coefficients or factors to translate it into kilograms of carbon dioxide equivalent. So it's really all takes any one of these pieces, and the common way is to translate it and sum it, all different parts of its life, into kilograms of carbon dioxide equivalent. So greenhouse gas, carbon dioxide equivalent. So, just to touch base where we are so far in this webinar, you've gotten some information, a bit of definition, some high-level topics. I put this on the information scale for a short webinar at 2 out of 10 of the useful information scale. A lot of you probably some generalized information. You may or may not, at least start with the topic. I at least had to phrase some of the main rules, but definitely in terms of useful info scale, we're somewhere on the 2 out of 10 range so far. So I'm not going to really bat around too much with the overall definitions. I will come back to target and goals a couple times in here because that's actually a major part of it that a lot of companies or people don't understand. Okay, so overview. We're looking at the greenhouse gas equivalents. Now I'm going to use it for mostly complex products like laboratory equipment or a medical device or a laptop or a cell phone. The example I'm going to use very specifically in here is we took a tablet from a mainstream vendor, supplier brand. We bought it ourselves and did it ourselves because we did it from publicly available products. I can sort of display bits and pieces. This is not necessarily their CO2 generation. It is relatively equivalent, actually, of their LCA. But I'm going to talk a little bit more specific. So we're looking at the greenhouse gas equivalents generated from the manufacturing and transportation of components. This is a really big part of it. This is everything down. So when you get a resistor or capacitor or a connector or lever arm, there's a lot of materials in it, metals, and it took a lot of energy and energy to forge to originally smelt that steel, forge it into that shape, transport it to you, etc. Same thing with the components. Your circuit board in particular is a very dense version of it. There's a lot of different materials there. If you ever done the plastics registry, you'd be amazed how much different plastics on your circuit board. A lot of energy is spent. The main source of greenhouse gas, there are a few others, is energy consumption. And to smelt or make steel, everything from original purification from the iron ore all the way to steel to make it into stainless steel or carbon steel or whatever, sucks up a lot of energy. Um, Hopefully the sound's all working through. I just got an interesting notification that my microphone's moved around. Hope everything worked out fine. Um, I'm gonna do a quick check. Anyways, I'm gonna see what's working right now. Let's hope. I am going to take a little pause and just slap on my Q&A. I need it later anyways, in case weird things are happening. Okay, perfect. I'm told my sound is great. Okay, good. Tell my mom. She thinks I don't enunciate properly. She's probably right, but again, don't tell my mom that. Um, okay, so it's also the energy used during assembly of the final product. So when you're actually putting, so you first have all these materials and metals and plastics, and it took energy. Then energy is the main contributor to CO2 gas, the generation of power, whether it's by coal, by nuclear, by hydroelectric, et cetera, solar. That's the main generator, main source of carbon dioxide equivalents. There are others, but that's the main sources is the energy consumption. So there's a lot of energy that's taken to originally make the steel and then forge the part and shape the part and put it all together. Um, then you actually have all the energy you use to actually put the machine together. So it's often at the facility, it's usually a relatively small amount of the energy. Usually you're building a whole bunch of machines in the same location. It's the energy used in the manufacturing floor to assemble and test the product. So you've already taken into account all the energy and the carbon dioxide equivalents generated from all the little bits that came. Now the energy it took to put all the bits together and test your equipment. And then, of course, the energy used in shipping. Now, in this case, electricity may be part of it, but you're more likely to see the contribution of direct combustion engines, airplanes, trains, trucks, etc. It's the energy used to ship the final product to the customer. So it includes all these, but it's not everything. Again, it's in the very, very start. The very, very start is, a rock comes out of the ground and starts being made into iron. The iron ore gets extracted, then smelted into iron, then to steel, then you eventually to parts and then a product and then you ship the product, and we're not done yet. This is still early in the lifetime of the product. You also have to include the greenhouse gas equivalents generated from the energy consumed during use of the product. I'm not sure if anybody's laboratory equipment has ever looked like that. Kind of made that myself for here. Definitely, if you've ever done LCMS, there is often some exotic piping, usually more even dicier looking plastic, not the metal there. Is the energy consumed during the use of the product. So if you have a laptop, like you might be using right now, and it's consuming energy, it's heat. It's actually probably not the hottest thing in your room. At this point in time, you're trying to look yourself in the mirror. Well, that too, I'm sure you're beautiful. It's usually the Wi-Fi router. It's hotter than you. I know you have to take this emotionally. Your Wi-Fi router is way hotter than you. If you take a infrared camera, which we have here, and you take it around your room or your office, the router is hotter than you. It's the hottest thing in your house, even more than often than your stove. Well, the inside of your stove will be way hotter, but on the average day, your router is the hottest thing in your house. And it consumes a lot of energy, as does your laptop. You might notice if you use your laptop on your lap for long periods of time, it's getting a little warm on the bottom. Its processor is a reason why it has heat sinks. It's consuming a reasonable amount of energy. Now, modern electronics like laptops, even tablets or cell phones are much more energy efficient for what they're doing than they used to, but they consume energy over the lifetime of the product. And then there's energy consumed and gases generated during the end of life of your product. So this is the end. You have to eventually take it somewhere, dismantle it, destroy it. Funnily enough, if you just take it in a truck and you dump it into a landfill, the actual, and your laptop's not going to turn into methane or carbon dioxide gases. The actual greenhouse gas equivalents generated from landfilling your product are basically zero outside of the truck to get it there. Recycling does take a bit of energy, and actually, strangely enough, recycling does contribute to your carbon dioxide generation. Very small. It's not a huge contributor. So general process, each contributor, and there's a lot of different contributors, has a kilogram of carbon dioxide equivalent value. And that value will often change by the source, by your jurisdiction. Different jurisdictions have different coefficients of like, so for each kilowatt, how many kilograms carbon dioxide equivalent? Maybe because the location has more coal plants than somewhere else has more, hydroelectric or nuclear, et cetera, which have lower CO2. And there are generally accepted equivalents or coefficients, factors that are created each year and updated. Now, if you did, you can actually use these coefficients. You just have to state you do these agreed upon ones. However, if you dig deep into it or you find in your second year, so when you do LCA, you often do it 1 year. This is where I am to have it, to meet often in a lot of tenders, the checkbox you have with the LCA. But then hopefully you've designed it, and I'll talk about that later, where you can figure out what the biggest contributors are so you can reduce it next year. And does the actual amount of what does 42 kilograms of carbon dioxide equivalent really mean? It's really intangible. What you really want to do is get a number, and maybe not the best number in the first year, and then figure out where the major levers are and spend effort on those one or two big contributors, and hopefully be able to say on your annual, environmental health and safety report for the company or whatever, we reduced our greenhouse gas equivalents of our products by 20%. And when you do that, you're really investigating more of the metals and the electronics, and you investigate deeply. There are abilities of a lot of suppliers to reduce them, and especially in the metal side. And there's opportunity for improvement. So you're often doing this because you need to, or a tender needs to, or there's a company directive to do so. But you want to structure it so these contribute these factors I'm going to talk about. You'll see that some of them are much bigger contributors at the end than others. And I'll show you some pie charts later, and then you can know, okay, next year, if I want to say I want to reduce this, I want to, justify my work, and everybody has to justify good work. This work would end up often in your corporate report at the end of the year saying, hey, we've reduced, or at least this product line, the greenhouse gases by 20%. The actual number of like 40 kilograms to 36 kilograms or whatever won't mean much to most people. Saying you've reduced it by 20%, that will mean something. So each metal or plastic per kilogram has some level of carbon dioxide equivalent, as does every transportation per kilometer. Air is different than truck. That's different than sea. That's different than rail, etc. They have agreed upon coefficients. Energy, it's usually jurisdictional, which jurisdiction. They have agreed upon coefficients for kilowatt hours. If you know more specifically on your supply source, whether it's nuclear or coal, etc., you can actually further differentiate it. Nuclear is obviously a much lower carbon dioxide equivalent than, say, a diesel energy generation or coal generation. And each type has, whether it's metal or plastic or material or transportation or energy source, have different coefficients or factors. So it's basically something, you take energy kilowatts times some kind of coefficient, and it gives you the kilogram carbon dioxide you're using. So it's usually, or each kilogram of stainless steel, this is the kilograms carbon dioxide equivalent, etc. Coefficients can be calculated for first principles. I don't recommend it. We have to do it in some cases. It's something you might do in second year, your second LCA, when you try and do reductions, when you're looking very specifically at your biggest metals and electronics and that kind of thing, where you might have some real ability if you drill down to reduce the number. So coefficients can be calculated from first principles, but normally annually updated standard coefficients are used to the point where, depending on what you're using, there's a number of different sources like EcoInvent, but also a lot of the jurisdictions, municipalities, cities, countries, etc., have different coefficients for certain things. They keep them up to date to different things. And one thing you're going to see in your coefficients is you're going to see differences between jurisdictions. Often it's time frame. We see the biggest difference is the annual reduction year over year is quite significant. So one of the things we looked at the tablet. We did the one we can talk about publicly, the LCA for, and compared against other tablets out there, and it agreed in proportions, but sometimes the carbon dioxide overall number didn't agree. And we found that the difference is the time frame, whether it was done this year or it was done 5 years ago or 10 years ago. The coefficients are very different. So a lot of the jurisdictions and different areas have different numbers because they're usually running at different times, or they've had a different person calculate it. There's a bit of variation that can happen there. Also, one thing you have to get used to is saying it's my coefficient, and I'll talk a little bit about that later, for steel, does it include transportation to the user? And so that does change things a tiny bit. So there's a little bit of digging and details. You'll find at the end of the day, there's a couple material types and uses that dominate over what you're doing. And so the key thing, if you're using coefficients from different sources, the key thing is you want to be truthful. And so if your number my US number differs from the industry number, which differs from the European number, state where you got it. Be honest. That's the key thing about LCA. It's not about hitting a certain number. It's doing this process with the purpose of improving in the future. So if you're using certain coefficients in certain places, all you do is you make sure you identify and list them in your final output. So I'll talk about the final output later. So useful information check. Where are we at today in the webinar? It's the webinar. It's better information, but I could have Googled this mostly. So I'd say we're about a 3 out of 10 in the useful information scale. I've given a lot more perspective, a little high level. Definitely talking about coefficients. May have actually bumped this up to at least a 3.5. Fine. Okay. Anyways, into more detail. Contribution from manufacturing and transportation of components. So this is often maybe one of the most significant contributors. It's the materials and metals and electronics, etc. All the carbon dioxide equivalents created by making them to the point where you're assembling them into final product. So it's the greenhouse gas from manufacturing, from transportation of the materials and the components to final assembly, which for something that's got metals in it, we're talking all the way back from it got pulled out of the ground as a rock, eventually got turned into a metal, into a pure metal, and then a particular alloy of metal, and then that metal got changed, cut up, changed in shape, and made into part of what you're using. Same with the plastics, which started, as oil pulled out of the ground and then refined and then processed into a typical resin. The resin then molded into shapes, etc. All and then eventually shipped to you. Now, strangely enough, you're going, that's a lot of things. Yeah, you can do if you do first principles, it's painful. There are times first principles means a little bit more. Where you're going, okay, it's not just steel, it's steel from that facility. Now let's talk to that facility and get a better number. And so that's a little bit different. So most of them, that's why I use coefficients. Somebody else has gone through the painstaking process of calculating the average version of that and updating it each year. And you reference where you got it. Like it's coming from this database or this source, or we use these sources. But they handle a lot of that painful bit. So on the bright side, you're not going to be the first person, I'm sorry, to ever calculate the LCA of a connector and the greenhouse gas emissions of a connector. A lot of people have. And a lot of people do it for regular business and update it every year. This is not the old school, like academic, doing everything first principles. It's not like that anymore. And one of the nice things about this, if you're going to be wrong, you want to be wrong like everyone else and state where you got it, where everyone else got it. If you're a real trailblazer, there's more you can do, especially if you're reducing. When you start reducing year over year, your greenhouse gas emission number, yes, you'll do a little more depth. But the nice thing is you're not doing the depth on everything. You won't be boiling the sea. You're going to be, fishing at the spot where you know the biggest fish are. So, biggest contributors from components, biggest greenhouse gas contributors are metals and dense electronics. So if you have lots of metal parts, they have very high coefficients per kilogram, and the dense electronics have a lot going on. There's a lot that happened to make the circuit board in, say, your tablet, your phone. There's a lot going on, or your laptop. There's a lot going on there. A lot of effort, work, energy was spent for that dense electronics. So those dense electronics will have higher numbers because there's a lot of energy to go with that complexity and detail and range of materials that makes up the dense electronics in your phone. The energy used during assembly of the final product. This is actually not very big usually. It's unless you do a lot of testing. It's the greenhouse gas from consumed during the final assembly and testing. So basically, if you're manufacturing the product or assembling it in a manufacturing floor, it's the energy of that facility that is doing the manufacturing component divided by the number of units manufactured in that facility per year or per month or however you're calculating the energy. So you'll often say, hey, we consumed X number of kilowatt hours in the manufacturing facility of these two product lines. This product line uses 40% of it, so it gets 40% of the energy, and we do 100 a month. So each one gets 1% of 40% of that facility's energy consumption associated with it. You might not be able to keep track of that math in your head, but it's basically, let's look at the energy consumed by the manufacturing floor of the product and what percentage of that floor does that one product use. in terms of, hey, I did 100 products this month and he uses 40% of the floor. So it's 40% of the energy consumed there. And then, of course, divided by 100 products. So, um, also escape refrigerant, which is not for everyone, but imagine you make refrigerators. It's not just energy, it is greenhouse gases. So if you're filling up, say, a centrifuge or refrigerator with refrigerants, if only 98% ends up in the machine and 2% ends up for a wander escapage, that escapage counts as part of your manufacturing greenhouse gas emissions, actually. By the way, this gets super extra complicated if your product has consumables. So if you're mega laboratory equipment that day does, I don't know, blood testing, and uses consumables and reagents, that can be included in or excluded. You just have to state that in your LCA. This is the LCA of the product, excluding the consumables, or you can say including. So you just have to be, of course, honest or truthful. If you have to state, if you're looking at giving the greenhouse gases for your entire business, yes, you'll have to keep the consumables in there. And that makes some of the other equations we'll talk about later a little more complicated. So final assembly contribution, you want to look at product transportation. How much does it take to get to the final place? It's greenhouse gases from the kilometers or miles of transportation to the final customer by truck, by rail, by air, by ship, by human, by bicycle, if that's true. Motorcycle. Actually, when I'm in Shanghai and such, it's neat. You buy a lot of things and they are delivered to you by a guy on a moped or similar. Um, so all of those count. Now, the biggest contributors normally are air travel. Now, the average customer is one thing you have to look at. So part of what you have to look at any of these things, what is the goal of the LCA? Well, the goal is like, I'm going to do an LCA. I'm like, that's actually not very specific. And I'll talk about goals. So the goal is a huge factor. So biggest truck travel is pretty big too. Goals. It's a very important part of LCA. So what's the target or goal? What do I mean by that? Goal questions. Okay, lifetime of the product. Is it X number of years? Now, the funny thing is you often want to use the average lifetime of the product, not how long it could last. Like a tablet often uses 3 years, even though it could still be perfectly functional for 10 years. Or the number of executions. This is a different way to look at it. You can look at it in years, or you can look at it, say, do the blood test, 1,000 tests, or our printer, 1,000 pages printed. You have to be honest in what you're doing, but is it by the number of executions or the number of years? When using consumables, your energy use is often related to how many times you do something. Or your laptop, it's usually how many hours you're actually running in that time period. So a little bit different. So number of executions can be the pages printed or tests run. And it's kind of a big deal with consumables because they have a huge factor. Like ink cartridges and that kind of thing actually do add up. So are you doing it for the lifetime of the product and figure out what's the average number of pages printed? Or are you going to do it saying our lifetime is this number of pages printed or LCA is for this number of tests run? Like this is the LCA for 1,000,000 tests run, etc. So for typical customer, also what's your typical customer? If you're saying you're shipping it to it, is it a customer in the EU? The standard has been generally, or up until now, being the customer being the EU. And you could say, yeah, I sell globally. That's fine. If you say, hey, I'm doing the average transportation to a customer in the EU, and I'm gonna write that in the notes down below is one of the like the coefficients and factors and all that kind of thing. We're using the average EU customer. Or because the California legislation, like SB 253, should use California. You can actually use EU or globally. You just have to state it. It will change the numbers only a little bit. Just globally gets more complicated. If you stick with one jurisdiction like EU or California, usually the transportation stuff is a lot easier. Otherwise, you're going, okay, let's figure out the transportation distance by type to, oh, I don't know, 10 different typical customers, and then what's percentage each one get, and black. So normally, you just be honest about it. We're going to say the average customer is in California, the average customer is in the EU. And you don't want to bias it too much. Like if my average customer is the guy 3 kilometers away from my manufacturing plant, okay, unless that's your main customer, not really. So you want to be somewhat still reasonable about it and not artificially inflate or deflate the numbers. Output, what's your goal? To have an output or to be able to improve or both? So a lot of people basically have a mandate, they have a tender or a company mandate saying you have to do one. Sweet. So you do one. One of the biggest advantages of doing one is you can make it better. And the make it better isn't like necessarily some lofty goal on making the environment better. It's the ability to say, hey, we've reduced our greenhouse gas emissions by our products by 10% this year. or whatever. You want to be able to say that percentage number and back it up with an LCA. That is probably one of the real business advantage of the LCA, not the actual calculation of like X number of kilograms carbon dioxide equivalent, which even me, who is an expert, doesn't has a tangibility gap there on what that really means. However, to show it's improved or reduced or be able to put in a bar graph, that is something that ends up in the corporate report. It's a different level of public information. So the ability to improve. So LCA's biggest advantage corporately is well, one, the checkbox if you need it to sell to somebody, but the other one is to be able to show improvement. It gives you a metricable, graphable thing that even the sales or senior executive, vice presidents, or investors, or whatever, think they understand the percentage change. Not the carbon dioxide equivalents, but the change in the number. It's very advantageous. All are valid. You just got to state in the final output what you're doing. So if you're saying, hey, I'm doing it for the average lifetime of the product, we're saying is 3 years, or I'm doing it per 1,000 iterations or papers printed, or my average customer, we're using California, etc. Fine, just state it. All valid, you just have to state it. Again, big part of LCA is it's not necessarily perfection, is doing that cradle to grave calculation and being honest all the pieces. We also got coefficients from this location, this location, this location. We followed these two standards, which I'll talk about later, and be honest about what you're doing. So the energy consumed during the lifetime, that's also a big contributor. And if you're a laptop, that's a huge contributor. Now, the energy consumed also gets really interesting for products that have consumables because that starts, it's not just the energy consumed alone, it's the fact that they use up consumables which have their own greenhouse gas. So let's say you take a printer and you have paper and you have a printer cartridge. They might say the paper is not us, that's somebody else, but the printer cartridge is ours. So the amount of printer cartridge they consume also gets added into this. But mostly it's the energy. It's like the kilowatt hours your laptop or tablet or medical device consumes during its use. So the greenhouse gas and power consumption of the product, and realistically, if it's using consumables, they're like added into the product's greenhouse gas ones. It's kind of like adding to the product itself. Nope. For a lot of things, average active versus standby is critical. A lot of products stay on 24 hours, but their consumption when they're active is very different than standby. So one of the reasons why a lot of consumer goods have standby power consumption limits because it's actually a huge factor and the product's not doing anything. Might still be on Wi-Fi though, or whichever, and that does consume, or it might, still cycle things or keep the lights on or whatever it's doing. So one of the things, and this is again one of the goals or targets or assumptions you put in the bottom is like, we're also assuming it's got active this many hours per day or per week, because business products are often quite a high per day, quite active during the week and not active on the weekends. They often do it by week instead of by day. And then how many hours per week are they in standby versus active? Big one is really the average number of active hours per week. And so it's kind of interesting. So whatever you use for the goals or assumptions, you just write that down in the assumptions section. And then it's also the energy consumed gases generated during the end of life of the product. So the recycling or landfilling. So the end of life. Nope. Recycling creates some greenhouse gases. The transportation and energy spent to dismantle and process and recycle creates greenhouse gases. Now, the funny thing is recycled metal, because it's already gone through all that mining and smelting, actually has a much lower greenhouse gas equivalent next time around than the virgin steel. So there's some advantages in the new product, but the product yourself, in part of your greenhouse gas, recycling does create greenhouse gases. It does reduce the greenhouse gases for the next guy's product that has recycled material in it, but it doesn't help you. Landfill creates very little for most products. It's the truck taking it with everything else, which is a very small amount of energy consumed, to the landfill, dumped in a hole. Your laptop doesn't create much for methane gases, and there's not a lot of energy used after that. So it's not really very environmentally friendly, but it's actually not a huge greenhouse gas emitter. What it doesn't do is it doesn't reduce the greenhouse gases for the next guy. So if you recycle the metals in your product, the next guy, actually, their recycled metal content, why recycled metal investigation in year 2 does make a big difference, is recycled metal has much lower greenhouse gas emissions because it's already been accounted for in many cases in the original virgin material. So where we are in useful information, This is better. Pictures helped. So we're probably a 6 out of 10 on the useful information scale. Kind of better. It's a webinar. Like, give me a break. It's only 30 minutes in. We're getting there. 6 out of 10 in 30 minutes is not bad. So how to do it? How do you actually do this? So couple notes. LCA are no longer custom academic knitting. I don't think we hate knitted projects. And what I mean by knitted is you doing it for the first time, knitting it by hand. It doesn't help anyone. It's work intensive, means more expensive for you, not as double checked, not as proven. You want processes that have been done, 100 times, 1,000 times. And when I first, saw presentations 18 years ago, when it was the realm of universities and academics, it was even before knitting. It was like trying to figure out what needles to use in the knitting. And now there are regularized processes. It's like an assembly line. And it goes really well with a lot of our processes. Canadian Plastics Registry and it are dovetailed together very well. It's a significantly more involved than the plastic registry, but the process flow has huge commonality because you're looking at materials. And then once you know all the materials, you can do a lot on the materials and components contributions, which is one of the most complex. Calculating it from the energy your product consumes during its lifetime is a bit of assumptions on how many active hours. On that, very straightforward. But all the different parts that make up your circuit board is much more complicated. And there are good ways to do that. There are regularized ways to do that now. So it's more of an assembly line process than it used to be. Standards, there are two standards, which if you read them, they will be somewhat helpful in terms of re-emphasizing a lot of what I've talked about is, put all the pieces together and there's a lot of high level contributions. There's a principles and framework one, and there's requirements and guidelines, ISO 4040 and ISO 4044. They're not that useful in actually doing the work. They are useful in structuring the work and in how you're going to do that. Overview, standards are very general. LCA processes have become much more regularized than what's in the standard. The standards you have to comply to the standards, which we do. But the standards are short and like, here is the flow chart and exactly how to do it but it provides a lot of the framework to make sure you know what's included and a lot of the guidelines on targets and goals and what you're trying to achieve. With greenhouse gas factors from regularized sources are updated every year. It's much more regularized. Like, so when you're working with, whether it's private sources like EcoInvent, which is a major one, or other database sources, or there's a lot of governmental sources. And for different things, different governments focus on different things. Like, you'd be amazed how much your state has on greenhouse gas factors. But you'll see, like, gee, there are a lot about asphalt. Yes, so the construction of roads is a major greenhouse gas factor, and for a city or a state, that it's a major calculation. And so they spend a lot more time looking at the greenhouse gases of different aggregates that make up your road, like the gravel and such. But they do also keep it up to date. So you also want to state where you're getting the sources. There's a lot more regularized says sources. I can turn that sources from sourced. We doing the first time you get these in the final version. By the way, everybody who registered, not just attended, but registered, will receive a copy of these slides with a fixed version, at least be a V2, and some of the English problems like sourced, which should be from regular sources, updated each year. Specific process. Well, so what we do everything in processes. You'd be amazed how many flowcharts and documentation we have here. Flowcharts that we find are much better for the person doing the job. However, the long version documentation is really good if somebody critical, had car trouble or whatever, and people have to learn things from scratch and go into detail. We have both. I'm a much bigger fan of the at the workstation instructions where you follow the flowcharts. We also have in-depth instructions for everything we do. So we have a questionnaire, and what the questionnaire is about, parts about goals, but things like lifetime of the product and how many active hours per week, and what's the energy consumption during active, and what's the energy consumption during standby, and what's the average kilometers by rail to the customer and by air, et cetera, et cetera, et cetera. So, and this handles most of the sections, the assembly, final assembly of the product, transportation, operation, and end of life of the product. The product approach is also then, okay, now we're going deep into materials. And there's a lot of different ways we do it. If you send one to our lab, especially if doing plastics registry, it's really easy. Otherwise, or your product's too big or expensive, you get big laboratory equipment, we have a questionnaire about what materials are in it, where you get to do a lot of the work for lots of fun. and then we take your materials information and do things with it. Now, we're not asking, hey, what's every plastic in your circuit board? You're not going to know that. What we're asking for complex assemblies is we have a lot of models, we've been doing this for a while, of what's in a circuit board, and we need to know how many kilograms of circuit board material and how many kilograms of cable. And those are more complicated materials, products, parts with lots of materials. We have a lot of data on that, and we can use. However, we won't necessarily know your outer housing is made from PPO or polyethylene or whatever. So if you take two tablets, it's funny, the materials difference between one tablet manufacturer and the other is almost exclusively the outer housing. Because the inner bits, even though they're dense electronics, are actually extraordinarily similar. The thing might do different things. It might have different software, so you might think it works very differently, but the actual materials used in one tablet from the other inside are almost identical. The outer housing is what makes them different. That one uses ABS, that one uses ABS polycarbonate, etc. That makes a much bigger difference. So the product level approach. So we handle one at the questionnaire level, energy consumption, travel, things that, you can get yourself. And then we have a different process, which also has two different methods to get the details about your materials and components. And then we turn that material and component data into carbon dioxide equivalent. We actually turn all of this into carbon dioxide equivalents. So we have two different streams. One is a questionnaire, which is around, the project questionnaire, which is around the product lifetime and shipping, and the one more about the product materials. And so two different pieces, they handle the five major parts of this. So when we do it, we also have two high-level approaches. We have a standalone service where we're doing quite a few for somebody who basically say, hey, I need to do an LCA for my product. Awesome. Let's do it. This is how we're going to do it. Or, which has become more and more common now, I say it's the majority of your LCA, is somebody else is testing a project with us for something else, especially plastic registry in Canada. Super straightforward to add to it. And it's a large fries with that. It's not that big of a variation for us. They're going, well, an LCA is very different than ROHS compliance. Yes, but we already have process to handle materials. And then, so what we need outside of the materials type stuff that we're really good at is we'll have a questionnaire for you to fill out on, average kilometers of ship to the final product and energy consumption in the assembly floor and lifetime of the product and things you can answer. Things often you can answer from the actual data sheet, your spec sheet of your product. And it makes it easy to put together. So if you can do things like Minnesota PFAS reporting, LCA isn't the end of the world. It's just having a plan. So add-on specifics, it's just a variation process from other projects. Like everything, we have flowcharts and instructions, and it's something we like to do. We like to do things, hundreds of times, not like once, and hope we cobbled it together. It's not a good process. And compared to doing 250 reach out SVHCs inside, a medical device, LCA is pretty straightforward, actually, in relative complexity. There's a lot of reach SVHCs. There's going to be a brand new one in 2 days. There's a 3 SVHC list updates this year, just for your excitement. One happens in 2 days or so, October 10th or so. That very likely, unless it gets denied, which is very unlikely, it's going to be the most common brominated flame retardant. You're going to have a 250, I think, first reach SVHC. I have trouble keeping track of the numbers in 2 days. But compared to doing that complexity, LCA is not that bad. It's work. So if you like any LCA added to any project we do for you, just ask. It's relatively straightforward. And if you know you're going to do it at some point in time, it's a lot. If you're doing a combination testing, it's a lot better. The accuracy of the data is fantastic. And it's a lot cheaper because we're already doing half the work, more or less, in terms of the heavy workload. So why not take advantage of that? And it might surprise you how straightforward it is. And getting approval is much easier. So the end output, this is the Excel version. The final version is in a Word version because it needs all the assumptions and everything. But this is more or less how it looks. There's lots and lots of data, different contributions. The pie charts are always the most interesting. This is just a tablet we purchased in the open market, did it ourselves. It's of no contribution from the actual manufacturer, other than the fact we used their data sheet. Their data sheet provides a lot of information. We made some average assumptions about transportation distances, but that was relatively straightforward. And shows the different components, the manufacturing, the manufacturing includes all the components in it. Very large contributor. The product use for a tablet, even though tablets are relatively energy efficient, it is fairly energy intensive. and looks at all that. And you actually look at the materials. The electronics are quite significant. Believe it or not, the packaging for this had a lot of significance because, and it might not be 100% correct, um, because it was the heavy amounts of boxes and stuff like that. So I haven't double checked the packaging side there. That looks a little high for packaging. Metals usually is a much bigger contributor. Electronics for a tablet will almost always be the dense electronics in the circuit board, and the display will dominate the materials part. So it's kind of what it looks like. And the output version will be in Word with all this kind of stuff in it, but has the references and goals saying, this is where the source of the coefficients are. The goals were an average lifetime of 3 years. We're assuming average customer in the EU, so on and so forth. All those different things. Active, the average number of active hours is this, number of standby is this, that kind of thing. So it has all the different assumptions. It follows ISO 14040 and 14044, etc. And this is the date it's done, and this is the revisions of the coefficients. Lots and lots of footnotes down the bottom. So now, why you have to do it, one of the reasons is it's a mandatory requirement of SB 253. So there's a hyperlink there. It's in California. It's for companies over $1 billion in revenue. Now, a lot of companies have been doing it for a while anyways, or have to do it, or have tenders that want it, especially in Europe. So starting in 2026, you have to do scope 1 emissions, which is not this. And it's from energy generated by the company, including company cars and any escaping refrigerants from your facility when it does manufacturing. And that's generally EH&S function. So it's often not a product steward or the product compliance person. It's more of a corporate EH&S function. Scope 2 emissions are also due in 2026 from energy purchased by the company, which will usually the biggest contributor. By the way, all this part's auditable, which means you need to keep the receipts. And this is generally EH&S function. And this is scope 1 and 2 are not the life cycle assessment. Starting in 2027, you need the scope 3, which is the greenhouse gas from the full life of your products. So full life cycle assessment, which is really product compliance. Now, you also sell a lot of services. You have to add that in too, but we'll just talk about the product side. This is often done by the product compliance prime, and then also includes the average employee commute and business travel, which again is more of an EH&S function. This is scope 3. This is the indirect. As opposed to energy use, it's the full contribution from your products and services over your lifetime, and travel of all things. Your average employee commute and business travel, but it's the LCA. The LCA that your product full life cycle, greenhouse gas emissions, your full life cycle of your products is the biggest contributor. It's how much your overall operations contribute. And again, there'll be a lot of assumptions, so you want to list all of those. So this is the 2027 timeframe where it's mandatory for large companies. However, it's generally becoming de facto mandatory because of the number of tenders that ask, hey, have you done an LCA of your product? The nice thing, you've done one, you're good for all of them. And then you want to look at year-over-year improvement, because that's the one that's going to be, the fact you calculate your greenhouse gas emissions will maybe be a footnote in your end of year corporate statement. You've reduced your greenhouse emissions, gas emissions of your products by 10%. That'll be a main headline in a section of your corporate end of year. So one of the big advantages once you create one is to be able to year 2, and that's good continued business for yourself and justification too, show that improvement, because that will actually be a top line item in at least the environmental section of your corporate report at the end of the year. Now, useful information check, where are we at right now? The whole picture is there, but we haven't given all the detail because, well, some people don't like to do math the whole time. I do a little bit, but not everybody. And there's a lot of detail missing. So I'd say we're out 8 out of 10 in useful information scale. If you want more, let's talk. Reach out. We do lots of this, and we talk specifically how we do it for your products. Everybody's product's a little bit different. Consumables have an impact on how you actually do it, or we're doing work for you already. It's really just incremental to add to whatever we're doing. So 2 major approaches. You stand alone, or if you just need an LCA, we can do it for you. Or we're doing something else for you. We can just do an LCA while we're at it. If you want to see what an LCA looks like, it's just added on. It's not like, oh no, it's then becomes a huge cost. No, it's mostly incremental. Again, like if we're doing Reach SVHCs, this one's not so bad. We've got Reach SVHCs, of course, down to a science, literally. The add-on specifics, it's just a variation process from other projects. Yes, it's got extra sections. Yes, it's got an extra questionnaire. Yes, we have to roll it up a little bit more at the end, but that's not terrible. And compared again to 250 Reach SVHCs, LCA is pretty straightforward. If you like an LCA added to your project, just ask. It's great. It might surprise you how straightforward it is. So Pretty well where I want to be schedule-wise. I thought it'd be a tiny bit shorter. If you have any questions, feel free to submit the control panel. Some good questions there already, and I'll try to get to as many as possible. If I don't get your question, or you have a different question, or you think of a question later, like in bed at 2 in the morning, don't be thinking about LCAs at 2 in the morning, by the way. But if you do, and you have a question, then email us or contact us later. We'd be happy to help. So people raise their hands, which is awesome. There's a Q&A. So if you don't want to put a question, there's a Q&A panel. Just put it in there. I'll try to get to as many as possible. Great question. Is the framework for calculating See, but I understand EPA and DEFRA have different calculators. Everybody has different coefficients. So what you want to do is whatever you're doing for the calculation, unless it says thou shall use, like tablets coming down from mountain, this method, most of them say just use ISO 14040, 1444. Then whatever calculation source you're using, or coefficient source, or factor source, reference it. Be honest about it. Say I'm using the ones from the US EPA, or I'm using one for EcoVent, or most of the time we use a combination thereof. There's many sources. Some are better than others. There's some beautiful ones at a state level that are a little over focused about stuff that goes into road, but they do have some good things that are not necessarily available everywhere else. Some people's products have material types that aren't as common, and you have to go a little farther afield. So you just want to state where you're getting the reference from. How can this reasonably be achieved for a company with hundreds of disparate products with thousands of related accessories? That's fantastic. So what you want to do is, again, what's your goal? I'm going to do the LCA for this model or product family. And if you want to say, hey, I got to calculate all of them together, what you normally do in year one is you go, this is my representative one. All the others we usually vary by their weight. Now they might, if transportation, if energy consumption during lifetime is a significant difference, we might add that in. But we basically create a model for, like we do for plastics registry or anything similar, for the representative item, and then use that to calculate all the rest and say, hey, in our approximation, we basically did this model and then we added in everything else we sold based on weight. If you want individual product level like declarations you can put online, what we normally do is you create a representative version and then you create variations based on its model. So you don't reinvent the wheel. You say basically, yes, this model has 75% of the energy consumption and 60% of the mass of the model X, where you spent the real effort, and it's just we're now going to calculate it based on that variation from the base model. So you always do a representative one and then use it to calculate, if you have to calculate the total, them together as a representative one, or if you can do individual product ones, you do a representative one and then you vary it. And you say, I'm just varying it, again, these parameters to create other individual ones if you need it. That can be time consuming. Like we do refrigerators, often refrigerator manufacturer oven might have, two major different types of fridges, two major different types of stoves, two different major types of dishwashers, a dryer. And that's like 5 representative models. But in the refrigerators, they might have like 30 different refrigerators based on those two structures, refrigerator or refrigerator freezer. So what we normally do is, okay, we do it for one refrigerator, and one refrigerator freezer, and then scale it for the others based on the difference in power consumption and by weight, and say they're basically the same materials, and we're just going to scale the weight contribution, materials contribution by weight, and the energy contribution by the average energy, and the transportation, again, by the average weight. And then there's some work, but you're not reinventing the wheel, and we just create it for the other. If you need individual ones for all 50 different refrigerators, then we just vary it from one model and then state that's what we're doing. Again, key thing is you want to be honest, and then you want to look at it saying, hey, if I want to bring this number down next year, where are my big levers? And if you saw the Excel graphs and stuff like that earlier, you're looking primarily at the electronics and the metals and the power consumption of the product. If the power consumption of the product's not going down next year, just harder to do, then you're looking going deeper into the metals or the electronics. Do you have any pricing models depending on the product complexity? Yes. It's strangely enough not. It's very simple. It's very similar to the plastic registry scaling, actually. To do the work takes effort. To do a much larger product takes more effort, but not proportionally so. So when in doubt, if you want pricing, just this is my product. How much? We'll tell you. Has LCA has been verified by an accredited body? There isn't ones for this. It's funnily enough, we do work for accredited organizations in this. It's really of the ISO. If you want to ISO 1404 to other accreditations, we can do that. Right now, it's just you state what standard you're doing it under. So that's a really interesting question. What you normally have to do for accreditation, there isn't really much for accreditation in this. Actually, it is normally you have to state why you're capable of doing it. If you need specific accreditation, there are ways to do it. We use Standard Council Canada for most of our accreditation. This one, normally we don't need it at this point in time, but you do have to state why you're qualified to do it. So that's what we normally have to do. Really good question. Any other questions? Is there a recommended way to report figures that demonstrate progress, even if business volume and GHG equivalent significantly increase significantly? Yes. So you want to state it honestly. And so if your advantage in what you've done for progress is a per unit basis, you want to state we've brought it down 10% per unit. Because if theoretically you've brought down the greenhouse gases by 10%, but you're doing 20% more volume, you're basically stating, yes, your numbers go up, even though you've done good work. So you want to make sure whatever you state is honest. And again, what your target or goal is. And we said, hey, and it could be we have brought down the average greenhouse gas emission by our two-door refrigerator by 10% this year. And you want to state, it's the average refrigerator, it's the two-door one, whatever is truthful and honest. That's one of the big things about LCA. The standards are pretty open as long as you do it honestly and truthfully and with double check your work and best efforts and all that kind of stuff. But the biggest one is to be open. Like if you look at different companies' LCAs online, you'll see huge variations in sort of the way they're done. They often come up with some different numbers, but the goals end up often being different. Like that my average customer in Europe versus China, or I'm doing mine on the print number of pages printed versus lifetime of the product, etc. So you want to be honest because people's products are different. If you have consumables, your goal or target lifetime is different because that printer cartridge is a contributor. And how you state that is 3 years of life. You could do 3 years of life, but then how many printer cards you're going through, which is fine. Or I can say it's X number of pages printed because that dictates my consumable use more than the number of years of lifetime. It's how many pages printed. And that's more correct from our point of view. And just state it for the greenhouse gas emissions because you're using consumables. And it is a big thing for consumables users where a lot of your greenhouse gas emissions is dependent on how much consumable you use, not how many years it exists. What you can do two ways. You can say, I can use on average this many consumables in a lifetime. That's fair. Or you can say, it's much more, we think it's more correct to look at number of pages printed or similar. So, or tests done. So it's always kind of an interesting way. So again, the big thing is if you're showing progress, be honest about it. But if it's your average unit, state it's your average unit. And and it might not be overall units, it might be we've reduced it of, our two-door fridges, whichever, and state it that way. It's a really good question. Any other questions? Perfect. Well, it's wonderful. And thanks again for everyone attending. There should be a recording of this available online in a day or two. And everybody registered will receive a copy of the slides. And great hosting everyone again. And look forward to hosting everyone again soon. And of course, if you haven't needed any help with LCA, especially if you're doing work with us right now, just ask. It's much easier to do in the midst of another project. It's just a variation in flow. Thanks again and talk to everyone again soon.